Aaron Group Tutorials. Learning made fun.
Everyone, today we'll be doing the roof bolt support. So we'll go through a few of the support mechanisms and then we attempt the question. So in general, there's 4 roof bolting mechanisms. We have the roof bolting mechanisms. So we have skin control. So with skin control, what you have a strong, massive, immediate rock. You have a strong, massive rock. So it's something like this. So you have your strong, massive rock. So this is what you have. These are your pillars. This is your mine opening. So there you have something like this. Let's say this is our roof. So there you have your strong, massive roof. That roof it can support itself. You have a strong, massive roof which is self-supporting. So what you do, remember, maybe you might be having cracks here and stuff and openings. Then you have your roof bolts here, roof bolts. So with this skin control, you're just trying to do what? You're just trying to prevent the loose rocks from falling at the skin of those openings. You're just trying to prevent loose rocks from falling there. So you can get much detail if you check maybe one of the books for rock mechanisms. So number 2, we have suspension control. Suspension, which is what we'll be focusing more on, suspension mechanism. So with suspension mechanism, you have a strong roof, a stronger rock unit, a strong rock overlying, sitting on top of a soft laminated rock. So what you're trying to do, you're trying to suspend the soft rock onto the hard rock, the strong rock. So you have your pillars, you have your opening. Let's say these are our pillars. Yeah, your pillars, something like that. Maybe let's say to divide and show the difference, maybe something like this. So the blue ones, this is our weak rock unit there. Then on top, you're having a strong rock unit. You see, so it's lying on top. It's lying on top of your soft rock. So for the soft rock to not fail, remember this rock can fail anytime. This one, the soft rock. We want to try and suspend it using roof bolts to the hard rock. Suspend it inside. Suspend it. So the hard rock, which is self-supporting, it can support itself. It's gonna hold this layer or these layers, depending on the situation. These layers of the soft rock. You see, but also the portion of the amount of the roof board that is inside the strong rock will also determine if our support will be effective. So we have to make sure that we determine how much is needed to be inside there. When more is inside that strong rock, it means the rock can be able to suspend a lot of weight of the soft rock. So the amount that is inside there, which is, we call it LA, it's our anchor length. The amount that is inside the hard rock, it's your LA, your anchor length. So if it's more, obviously it will mean that the rock will hold more. So the more of LA, the more this thing can hold. Then obviously this one is just your length of your bolt. Then this is just your spacing of the bolt, SB. You see. So that's what we have with this one. You have a stronger rock unit sitting on top of a soft rock. Then number 3, we have your beam building. So I won't go much into details in these ones. So we have beam building here. Let's do this. So with beam building, you have blocks of fractured rocks on the roof, sitting on the roof. Blocks of fractured rocks there, but there's no self-supporting rock there. You see. So what you are forced to do with beam building, you're still gonna use your roof bolts, but now what you're trying to do, those roof bolts, they're just trying to maintain friction on the bearing planes, because that rock will be having bearing planes there, but it is not self-supporting. There's no self-supporting beam. So yeah, just go and try and look at the details with this one. Then number 4, we have supplemental. When you're supplementing, you're just adding extra on top of what's there. So with this one, you'll find that you have support, you have roof bolts, but they are not holding the rock. The rock is extremely weak. It's fractured, like it's maybe destroyed. So you put some maybe W straps maybe there just to hold that thing. See, you have your roof bolts maybe there. You're putting some straps to try and hold this block of weak rock. So you're just trying to prevent this rock from just raveling here. You see. But our focus is with this one. It's on this one, the suspension mechanism. We'll be designing support based on the suspension mechanism. So now let's go and do an attempted question. So what you're gonna have, let's see. So what you're gonna have, so this is our question here, but we'll be doing question number 3, then we'll come back on these other questions. So we'll be doing question number 3, but we'll be taking information of us from the top there at number 1. So we are being asked to design a support. Number 3 is saying if the sandstone in question 1 and question 2 is 1.5 meters thick and underlain by laminated shade and mudstone. So you're supposed to design support for this. So we're going to do number 3. So you can take a screenshot or try and pause the video. Take a screenshot because we're gonna exit from this this picture here. But this is the question that we'll be doing here. So I'm just gonna write the data down, and then we can start with the question. So okay, we're given that in that question, we're given that the sandstone tensile strength. So I'll just say sandstone. So we're given that the sandstone tensile strength. So sandstone tensile strength, it is right here. We're told that it's 5 megapascals, 5 megapascals. Then we're also told that the density of sandstone, density, is equals to 2.5 tons per meter cubed. Okay, we're also told that okay, let's see, what else are we given? Oh, we're given the road width. So we're given the road width, it's equals to, they are equals to 6.5 meters. Then the resin or rock resistance or rock shear resistance is equals to 2.5 megapascals. Then we're also given the bolt diameter. So the bolt diameter is 20 millimeters. Then the drill hole diameter is 28 millimeters. Then the steel tensile is equals to 550 megapascals. Okay, from that picture, this is the data that we have. This is the data that we managed to take out from that picture. Sandstone density, the road width, the shear resistance, and then we have the bolt diameter to load. This is what we have. So we're gonna use this and try to design support for this environment. So the first thing that you do when you're designing support using suspension mechanism, remember we are using suspension mechanism. We have to determine the minimum thickness of the competent beam, which is that hard rock sitting on top. Remember I said in suspension mechanism you have a stronger rock unit sitting on top of a soft rock unit, overlying a soft rock unit. For the soft rock to not fall, it must be suspended. It must be held by the hard rock. So we're going to drill our roof bolts so that they reach the hard rock part, and then they suspend the soft rock. So we have something like this, something like this. So that's your hard rock. Remember, that's your strong hard rock. That's your sandstone in this case. Then below this, okay, they said the thickness here for this is 1.5 meters. Then below this we have layers of laminated shale and mudstone bands. So I'll just put them as one thing, because I'll just put them as one thing. So we have our soft rock there, it's laminated. So we just say this thickness of these soft rocks we're given as 15, 10, 5, 10, yeah. So you're just gonna add them and convert to meters. So we're getting our thickness as 0.6 meters for this soft part. So now we're gonna try and determine the minimum thickness and compare it to the thickness that we have. Remember, the minimum thickness, at least our thickness that we have for the suspension mechanism to work, the minimum thickness that is required for this thing to work, the T that we're gonna get must be at least less than what we have or equal to what we have. If it's greater than what we have, it's gonna be a problem. But yeah. So let's continue. What we have to determine the minimum thickness required, we're gonna use this formula here. You're gonna have, okay, the first step, it's a minimum thickness required for this thing to work. How much do we need for this hard rock to be able to suspend the weight of these soft rocks? So it's T is equals to N, then you have your R squared F over 2 times QT. So now we need to find our N, because you see our formula has an N there. So to find N is just equals to 1 plus T soft over T stiff. So we're going to have 1 plus the thickness of the T soft, it's 0.6. We found it here. So it's 0.6. T stiff, it's 1.5. So 1.5. So what do we get? 1 plus 0.6 over 1.5. So we're getting 1.4 is our N. So we just come here and substitute. So you're gonna have 1.4. Your L is those road widths there. You see, it's that part that we cut out. So it's like the maximum self-supporting span. You can see it. It's the L. So our L we're given as the road width there. It's 6.5. It's what determines how much are we gonna cut our rock to get the road width, by how much. So we're given it as 6.5 then squared. Then this y, this thing that looks like y here, it's gamma. What? It's your unit weight. So it's gonna be your weight in your density in kilograms per second per meter cubed times 9.81. So we're given our density in tons. So to convert it to kilograms, it's gonna be 2.5 kg per meter cubed. So it's just gonna be that times 9,81 for our y, the thing that looks like y, the gamma there. So it's 2.5 times 9,81. F, it's your factor of safety. So in our question, we're given our factor of safety. If you took a screenshot there, the factor of safety was given as 2. So let me write it down here. Factor of safety, we're given it as 2. So you put your 2 there over 2 times our tensile strength of the sandstone. We're given as 5 there. It's 5 megapascals. So it's gonna be 5 times 10. You want it in pascals. Then we get our thickness. So 1.4, 6.5 squared, 2,500 times 9,81, 2 times 10 to the power of 6. So we're getting 0,29 meters. So this thickness here, it's less than what we have. We're 1.5. That 1.5 is more than enough to assist us with this suspension mechanism. So the 1.5 meters that we have is greater than the 0.29, which is required. Therefore, more than enough thickness. We have more than enough thickness for suspension. It's more than enough to suspend that thing. So now we go and calculate what? The spacing of the bolts, our SB. So the spacing of the bolt spacing, the bolt spacing. So the formula is SB is equals to the root of 2 TA, and then you have your tensile, then your N. That's what you have. So remember, we have everything here except T average. So to find T average, you're just gonna add those layers one by one. But it's for the soft rock. T average is for the soft rock. Let me put it here. T average is for the soft rock. Let me just write it. TA, it's laminated rock, the soft one, is equals to. So for the soft rock, they told us that we have 15 centimeters, which is 0.15. So we have 0.15 plus. Okay, that's what we have. So you have your soft rock layers. We added them divided by 5 because they are 5. So it's 0.15 plus 0.1 plus 0.05 plus 0.1 plus 0.2 divided by 5. So we have 0.12 meters is our T average. Okay, so this is what you have. So you have your 2 times 0.12, your 5 times 10 to the power of 6, which we're given is our tensile strength. Then our N, we found it as 1,4. Then this, I said, it's just your density in kilograms per meter cube times your 9,81. So it's 2.5 times 9,81 times your factor of safety of 2. Then you get your spacing. Let's just write it down here. So our spacing, bolt spacing, 2 times 0.12, 5 times 10 to the power of 6 over 1.4, 2,500 times 9,82. So we're getting a value of 4,18 meters. So we're getting our SB being equals to what? It's around 4.2, or just say 4.2 meters. This is the spacing suitable for this environment. We are here to buy. We're gonna buy a bolt. We're gonna buy a specific bolt with a specific properties. So we're gonna try and compare the bolt that we have to this spacing. Remember, this is just the general spacing for the environment that we have. We're still going to find our SF, which is the spacing that our board that we have purchased can take. How much space can our board that we have allow? This one is just a basic space, general space for the specific environment. So now we go and find our bolt length. Number 3, while finding our bolt length, remember we're still designing the support for this environment. At the end, we're supposed to have specifics. We're supposed to tell the person or the company that, okay, guys, you can buy bolts of this length, and they can also space them with this specific distance. Okay, so now we are finding our bolt length. So to find the bolt length, you're going to have your LB, which is your bolt length, being equal to your TLM plus your anchor length. Remember, this is the case that we have. We have something like this. Okay, we have our pillars, then we have something like this. Okay, let's say we have our strong rock there. That's our sandstone. Then those laminated, what they are here. So we have your laminated what. So this is our soft layer, soft part. That's our strong part. So you're gonna have your bolts driving through here, entering there. Then the next one, something like this. So our TLM, our bolt, our TLM, it's this portion here. The thickness of the soft rock, which makes sense for our bolt length to be equal to a TLM plus the anchor length, because you have your TLM here, then you have your anchor length there, that portion where that's inside the hard rock. So you're gonna have your bolt must be sufficient enough to have a length that is greater than the TLM, and then it should also have an anchor length there entering the hard rock. So what you have, you're gonna have your TLM, which is your average for the soft rock, and we found it as what? It's 0.12. No, not the average, our thickness. What's our thickness for soft rock? It's 0.6. So it's 0.6 plus your LA. You have to find your LA. There's a formula for LA. So for LA, the formula for LA is equals to this, and our spacing, our TLM over pi, our diameter. Okay, this is the diameter of the hole, and then our shear resistance. So this white thing there, the gamma, already have it as 2.5 times 9.81. Your spacing, your SB, you found it as 4.18. Let me just stick to 4.18 instead of taking the rounded up number. So we just take 4.18 squared. Our TLM, 0.6. The average of the soft part. Pi, the diameter of the hole we given there in the question. It was given as the real hole diameter, which is 28 millimeters. So we're supposed to divide it by, convert it to meters. So it's gonna be 0.028, 28 divided by 1000. Yeah, it's 0.028. Shear resistance we're given. Rock to resin shear resistance is 2.5. So you're gonna have your 2.5 times 10 to the power of 6. Then we get our LAs. 2.5 times 9.81, 4.18 squared, 0.6 over pi, 0.028, 2.5 times 10 to the power of 6. So we're getting 169. I'll just take 3 numbers. So yeah, it's 1,169 plus, so that number plus 0.6. So we're getting 1.1 almost 1.8, 1.7. So it's 1.8 meters for the bolt length. So now the last part, you're gonna do your SF. Yeah, you have now bought the bolt. You wanna compare it to the general SB. So now you're trying to check the adequacy of the steel that you have. So your SF, so we're checking the adequacy here. Adequacy of the steel that we have. So maybe we decided to buy cheap bolts. This calculation is going to tell us this bolts they won't support this spacing of SB. Remember, for SB you got 4.2. For cheap bolts, when you're calculating for SF, you might find that it's giving you a smaller number than the SB, meaning it's saying the environment that you are in, based on the bolt that you have now in your possession, that bolt won't be able to sustain a spacing of 4 point something, because we got 4.2, I think. You see, but if your SF, the number that you get here, is greater than our SB, it means that our bolt can actually perform more than what we can anticipate, because the SF, remember, it's for the bolt that you have. If the SF is greater than the SB, the general spacing for the ground conditions in that environment, it means your bolt is actually more competent, it's very strong, it's a proper bolt. So now your SF is equals to diameter of the bolt pi QB 4F, then this TLM. So the diameter of the bolt was given as what? We're given as the as 20. So it's 0.02. So it's gonna be 0.02 square root, then your pi. This one, it's the steel, it's this one, steel tensile, which is 550. It's no longer the sandstone, it's QB for the bolt, B for bolt. So it's given as what? 550. We're given 550. So you're gonna have 550 times 10 to the power of 6 over 4 times a factor of safety of 2. Then this one is the same thing that we've been doing. The TLM is 0.6. So now we're gonna get our SF. We're getting our SF as 0.02 pi 550 times 10 to the power of 6. 4 times 2, 2.5 times 9,81. So we're getting it as 2.42, which is 2.4 meters. So if you check here, remember our SB was equals to 4 point. How much did you get for our SB? How much did we get for SB? We got, let me see. We got 4.2. So SB was 4.2 meters, but our SF is giving us 2.4. It means our bolts can survive in a spacing that is less than that 4.2. Our bolt that we have can only survive in spacing that is at least less than that 4.2. At least must be 2.4 or less for this bolt to survive, to function at its optimum best. So now the moment our spacing increases beyond 2.4, our bolt will fail. So we're just gonna take the SF. You take the smallest number here when I recommend you. So your final answer, you should say, when I recommending to the manager or the company. So your bolt spacing, you'll tell them that they should take bolt spacing of 2.4. The smallest number between SF and SB, that's what you take. Then your length, you take what you got. So your length of the bolt, we found I think it was 1.8. Let me see. Yeah. So 1.8 meters. Then you are done. Then you get your 30 marks or your 25 marks. Let's see. Yeah, we are done.